Welcome to the next lecture of the CBNST. In today's lesson, we will learn another formula to solve algebraic and transcendental equations. And today we will talk about iterative method or method of successive approximations. In the previous lessons, we have already done the bisection method and regular falsi method. So let us see how we can solve the algebraic and transcendental equations using this iterative method or successive approximation. So let's first see, if one equation is represented by fx is equal to 0, then what we have to do, we have to rewrite this equation in the form of x is equal to phi of x dash. So we need to convert this equation into x is equal to phi of x dash, and then we will identify our first approximation root. We will replace the first approximation root into this first equation. That will become our first iteration. So let us see if we find our first approximation root, that we can find out with the help of the halving method, that is a plus b by 2, where a comma b will be the interval of the given function. So let's say if the first initial value will be x0, then we can obtain x1 as phi of x0. So this will be our first iteration, and in the same way we can continue. That means we can achieve x2, the second approximation root, by phi of x1. So this will be our second iteration. So this will continue, and we can find out x3 by phi of x2, and so on. In the same way we can achieve xn is equal to phi of xn minus 1. So we can find out till desired accuracy. We will find out the root. So now let's understand this method with the graphical form. Let us imagine, okay, right, this is the x-axis, this is y-axis, and this is the line x is equal to y. And you can see this is the curve, this is fx. So this is representing our actual function, that is the algebraic or transcendental function equation. Let us say that we have x0 as our initial approximation. Then we will draw a perpendicular from this x0, which will cut the curve at some point. Now this point will be known as f at x0. From this intersection point, we will draw a parallel line to the x-axis. So we need to draw a parallel line from this point, the parallel line to the x-axis. This parallel line will cut this line x is equal to y at some point. From that point, again we will draw a parallel line to the y-axis, or we can say we will drop a perpendicular onto the x-axis. So let's draw a perpendicular onto the x-axis, or we can say let's draw a parallel line to the y-axis. So once we draw the parallel line, this parallel line obviously will cut the curve at some point. And this will be our next approximation root. So you can see this is our next approximation root. This next approximation root is cutting the function, that is the curve, at some point which is f of x1. Now from this point, again we'll iterate, we'll perform the same steps again. We need to draw a parallel line to the x-axis, or we can say we will draw a perpendicular to the y-axis. So let's draw a parallel line to the x-axis. Now this parallel line to the x-axis will intersect this x is equal to y line somewhere at point like this. From this point, we need to draw a perpendicular to the x-axis, or we can say a parallel line to the y-axis. So let's draw a perpendicular to the x-axis, and we'll extend this upwards so that it will cut the actual curve at some point. So now this is our new approximation root, that is x2, and this x2 is cutting this curve The perpendicular is intersecting this curve, and this point will be known as f at x. So this process will continue. So let me draw another parallel line to this x-axis from this point. So this will be the parallel line which is cutting the x is equal to y line at some point, and from this point we will draw a perpendicular to the x-axis. This will be our new approximation, that is x3, and this point which is at a curve will be known as f at x3. In this way we can see we are converging towards our actual root. So this is our iterative method or successive approximation method. Now let's solve a numerical on this. So as we can see that we have a function written here, that is fx is equal to x cube minus 2x square minus 4 is equal to 0. So we will begin with the first step, as we have done into the bisection as well as into the regular falsi method. We would try to find out the interval such that we have to find out an interval a comma b such that at a and at b the signs of the function are opposite. So these both attain opposite values, opposite signs. At fa, if it is positive, then at fb it should be negative, and if it is at fa positive, then it should be at fb it should be negative. So let's use the hidden try method. First of all, we would like to substitute 0 into this particular given function. So let's substitute 0 in the given equation. So now this is f at 0. This will be 0 minus 2 into 0 minus 4. So now this we can see the value, this is vanishing, this is vanishing. So this is minus 4, basically a negative value. Now let's substitute 1 in this equation at x. So if this is 1, so this is 1, minus 2 into 1, minus 4, this is equal to 0. So now we have this is 1 minus 2 minus 4. So this is coming minus of 5. Again a negative value. We need to move further. So we will substitute f at let's say 2. So in this case this is 2 cube minus 2 into 2 square minus 4. This is equal to right, this is equal to, let me solve this. This is 2 cube, this is also 2 cube. Positive and negative cancel out. This is minus of 4. Again a negative value. See, we have not got other positive value till now. Let's move further. Let us substitute 3. So if it is 3, then we have 3 cube minus 2 into 3 square minus 4. This is equal to 0. So now let me solve it. 3 3s are 9, and this is 27 minus 3 3s are 9, 9 2s are 18. This is minus of 4. So now this is coming 18 and 4. This is 22. 27 minus 22, that is 5. So now we have got a positive value. So now you can see at f, the function's value at 2 is negative and function's value at 3 is positive. So we have got that initial interval, and that initial interval in our case is 2 comma 3. So this is the first step of finding out the initial interval. But in this case, iterative method, we need only a single initial approximation. So how we will do that single initial approximation? We can take any value in between 2 and 3. We can take 2, we can take 3, we can take 2.1, we can take 2.2, 2.5, 2.9, any value in between 2 and 3 we can take as our first initial approximation. But I'll always suggest that take the midpoint of this interval as your first initial approximation. So let me take the mid value of this 2 comma 3. The mid value of this 2 comma 3 will be 2.5. So our first approximated root is equal to 2 plus 3 by 2. This is 2.5. So I'll take x0 as 2.5. So this is our second step. Now let's write the third step. We need to rewrite this function in this form. So we need to represent this as x is equal to some function. So let me do this. We can say that this is x cube minus 2x square minus 4 is equal to 0. So we change this in this way. So we take this portion to the right hand side. This will be 2x square plus 4, and now this x will be equal to 2x square plus 4 to the power 1 upon 3. As this is x cube, so whenever we convert this into x, this will be 2x square plus 4 to the whole power 1 upon 3. So this is the representation we want to have. Now this is what x is equal to phi dash of x. We will use this and we will start our iterations. So let me use this and continue with the iteration thing. So let me write it again, that this can be represented as x is equal to 2x square plus 4 to the whole power 1 upon 3. Now let's begin with our first iteration. So the first iteration in which we will get x1, this will be 2. Instead of x, we will substitute x0. So this is x0 square plus 4 to the whole power 1 upon 3. This is twice of, now what was x0? 2.5. So into 2.5 square plus 4 to the whole power 1 upon 3. So now here the value of x1, so now let me see the value of x1, that is at 2.5 is equal to 2.5458. So this is 2.5458, and this will behave our next approximation. So now the next iteration comes into the action. This is x2. So now x2 is twice of x1 square plus 4 to the whole power 1 upon 3. Now we continue. This is twice into, what is x1? The x1 is 2.5458. This is 2.5458 square plus 4 to the whole power 1 upon 3. Obviously we will be using the scientific calculators to solve this. You must be aware how to use scientific calculator. You must use proper brackets and BODMAS to achieve your result. So let me see what is the x2 with the help of the scientific calculator. So this x2 is 2.56937. So this is 2.56937. This is our x2. Let's perform another iteration, that is the iteration number 3, x3. Obviously what will be x3? x3 will be twice of x2 square plus 4 to the whole power 1 upon 3. Now this will be twice into, what was x2? We have just calculated x2 into our previous iteration. The value of x2 is 2.56937. So this is 2.56937 square plus 4 whole power 1 upon 3. So now what will be the value of this x3? The value of this x3 is 2.58149. So this is 2.58149. This is at our third iteration. Now the question is when we will stop doing this. So as I have already told you, there are two ways of stopping this depending upon the question. Either we have a limited number of iterations, let's say we have to perform 5 iterations will be given in the question, or we have to perform 10 iterations, or the second way is we have to give the result to some desired accuracy. So let us see what is the desired accuracy till now. If we compare the approximated values, let's say x3 and x2, the last two values, so we can see here it is 2.58149 and it is 2.56937. After decimal, only one digit is matching. So that means we have got the result after one decimal place only. And in the examination, you could have been asked that you have to find out till 3 correct decimal places. So you will have to continue this till after decimal 3 digits matches into your last two approximation roots. So you have to continue this with, let's say, x4, x5 and so on. So let me write the values of these onto the further iterations. So we have already seen till iteration number 3. let me show you what is iteration number 4, that is the value of x 4, then iteration 5, that is x5, iteration number 6, that is x6. I already have these values. You can calculate with the same method, you can calculate with a similar way. So now this x4 is 2.58772, so this is 2.58772. Then the next is x5 is 2.59092, this is 2.59092, and at iteration number 6 we have 2.59 2.59211. So now you can see after iteration 6, if we'll analyze the last two iterations 6 and 5, we can see that 2.59. So now we have the desired result accuracy to two decimal places, after two decimal places. So in the same way you can find out the result of any of these algebraic and transcendental equations. There is an important term called convergence of the method. So I'll talk about the convergence of the methods like bisection, regular falsi, and this method, and all the other methods we are talking about in a separate lesson. And I'll be giving you a comparative analysis of all these methods into that separate lesson. Thank you so much.